Hello everyone and welcome to lecture number 2. Today I'd like to go over some basic summary of models using differential equations. And I'll talk about some general ideas with modeling using differential equations, as well as go over some specific examples from population growth, specifically the Malthus model and the Verhulst model of population growth. And I'm also going to talk about some first-order ordinary differential equations theory that you should hopefully be familiar with from your differential equations class, but just I'll review a little bit of it. So to start off, in general, the mathematical methods that we use from model to model are extremely varied and range from very simple to very advanced. But typically, when we're doing continuous problems and continuous modeling, it often involves finding an exact or approximate solution of some kind of differential equations. And a differential equation is an equation relating the derivatives of several unknown functions, the dependent variables, to the independent variables of the problem. And probably the most important thing to do is to study all of the different classifications and become very, very familiar with the classifications that differential equations fall into. A differential equation is said to be sometimes just for short, known as DE, is said to be linear if every dependent variable and its derivatives appear linearly in the differential equation. And likewise, a differential equation is nonlinear if this does not happen. So if at least one dependent variable or its derivatives appear nonlinearly. In the differential equation. And in general, linear differential equations are easier to find solutions for, which is very, very nice. And easier to find both analytical solutions and numerical solutions. And nonlinear differential equations are much, much more difficult and more nuanced when it comes to solving for. So this generally applies to both analytical and numerical or computational simulations or solutions to our differential equations. Unfortunately, in applications, the best and most accurate models are typically nonlinear models. I guess it's not really too unfortunate because it provides a very, very rich avenue for research and understanding of real physical problems. But when it comes to applications, the more realistic, more accurate models tend to be nonlinear models. which are much harder to solve for in general. So the first, I shouldn't say the first, the next main classification that we have is the classification between partial differential equations and ordinary differential equations. So we'll start by talking about partial differential equations. Or PDEs, as they're sometimes called. So PDEs are differential equations with more than one independent variable. So we have a number of different examples of partial differential equations. I'll start off with two very, very nice examples, both exemplifying the linearity and nonlinearity considerations we just talked about. So if u is a function, u is the dependent variable in all of the examples that I'm going to do. We can talk about the one-dimensional wave equation, and obviously for more complicated scenarios it's going to become more complicated, but whenever someone talks about the one-dimensional wave equation, they're typically talking about this equation right here. And c here is called the velocity, or the speed of the wave, the traveling wave. And u is the dependent variable in this problem. This is the 1D wave equation. This is in 1D. And it governs disturbances that propagate with speed c along one spatial dimension as a function of time. So in this case, u is a function of both space and time. The dependent variable u is the disturbance, and it depends on time and on space. Likewise, we can actually derive the wave equation in any number of variables. The wave equation 2D is the second partial derivative of e with respect to t equals the wave speed c squared times the second partial derivative of u with respect to x plus the second partial derivative of u with respect to y. In which case u, in this case, in 2D, is a function of x, y, and t. And lastly, we can talk about the wave equation in 3 dimensions, which is a function of 4 variables, t, x, y, and z, and it's saying that the second derivative of this function u, the wave propagation, or the wave disturbance, second time derivative is equal to the wave speed squared multiplied by the sum of the second partial derivative of the disturbance with respect to x, y, and z. So this is sometimes called the standard wave equation, where c is a constant, called the wave speed. This is a very, very nice kind of picture, whether you look at it in 1D, 2D, or 3D, but this is a linear PDE. And that is unless c is not constant. C is something more complicated, like unless C is a function of u, ux, uy, uz, or ut. In which case it would not be a linear wave equation anymore. It would be a much more complicated PDE. So the next example that I want to talk about is what's called the KdV equation. It's abbreviated as the KdV equation, but this stands for Korteweg-de Vries equation. And this is actually an equation that is a mathematical model of waves on a shallow water surface. The derivation of this equation is rather complicated, so I'm only going to write down the 1D version. Even that's kind of complicated. But this equation is the partial derivative of u with respect to t plus u times partial derivative of u with respect to x plus the third derivative of u with respect to x equals 0. The KdV equation is a very, very standard example of a nonlinear partial differential equation. And this is a good classifying like this is a great practice to get into and to understand. But specifically, the nonlinearity is this term right here, because you have a quadratic term where you have the solution multiplied by the derivative of the solution, partial derivative of the solution. So this is the nonlinearity in the KdV equation. And you might not believe it, but this complicates things a lot, especially for PDEs. Even linear PDE theory takes a little bit of time to develop and to understand how to solve correctly linear PDEs. That's why there's a whole couple of courses on it, both undergraduate and graduate, on solving PDEs themselves. But even so, going from linear to nonlinear PDE is very, very, very difficult. But we'll see by the end of this course that we will be able to figure out how to solve the KdV equation and similar types of equations through use of certain methods that we can develop in the course. But mainly, they're both technically types of wave equations. The typical wave equation is a linear wave equation, and the KdV equation is like a modified kind of more general nonlinear wave equation, but this describes what's called Russell's solitary wave phenomena. And we will actually see in the class that it can be solved analytically. And the experiment by Russell was very, very interesting and exciting. If you look back on the history of how this equation was developed, but the solutions are actually what are called solitons, and we'll see soliton solutions. Generally, when we're making models, we don't just even get single PDEs, we get what are called systems of PDEs. So a system of PDEs is a system of such equations. So when you have multiple dependent variables and multiple independent variables, each of which are related to one another through a complicated system in terms of the partial derivatives, you have a system of partial differential equations. Each one of these partial differential equations is an example of a single partial differential equation. So I'm not going to write down exactly the general form for a system. We will talk about it a little bit later on, but some examples of systems of PDEs include Maxwell's equations of electrodynamics, the equations that govern the propagation of light, and electromagnetic fields, the Navier-Stokes equations of fluid mechanics, which are extremely important from a computational standpoint. If you want to say solve for the fluid flow over an airplane wing, or fluid flow over a race car that you're modeling, or a boat, or many other very important applied phenomena, or even what are called the Euler equations of gas dynamics. These are all examples of nonlinear systems of PDEs, which are extremely important and are solving them in general in the full 3 dimensions of space plus time is very, very, very difficult, and is still an open problem for these scenarios. The Navier-Stokes equation is actually $1 million prize offered up by the Clay Mathematics Institute if you can prove or disprove the existence of such solutions in 3 dimensions of space plus time. So it's a very, very, very difficult problem to prove anything about these in general analytically. But a single PDE of this form, so a single PDE of this form, and we can see this up here in these examples. Each one of these examples can be written as a function of the u and its derivatives, and possibly of all of the independent variables as well. So it's a multivariable function of these set equal to 0. So it's some function f. We do f of all of the independent variables. So f is a function of x1 and possibly all of the independent variables up to k. If we have k independent variables, it's possibly a function of all of the derivatives of u with respect to x, where u is the solution. Up to xk, it's a function of the second derivatives. And this is including the mixed partial derivatives, the second mixed partial derivatives, all the way up to and including the second derivative of xk. So for these derivatives, you have k total. These derivatives, you have k squared total, because all of the second mixed partials. You can actually reduce that because of if you can prove that it's continuous of the second partial derivatives are continuous functions by Clairault's theorem, the mixed partials are going to be equal to one another. But the idea is that we have to continue this all the way up until we get to the highest order derivatives. So the nth order derivatives, partial derivatives of u with respect to x1, and all of the possible combinations of all of the derivatives of all the variables. So as you see, in general, a general PDE can be a very, very complicated thing. But the idea is that in general it's a function like this. And solving it involves solving for a function u that satisfies this for every single point in every single one of the independent variables. So for every point in the domain. So the next classification that we can make is the order of the PDE. And you might be familiar with some of these classifications from a previous class. I just want to make sure that everyone is on the same page. So the order of a differential equation is the highest derivative order appearing in the differential equation. We go up and look at the wave equation. The wave equation is a second order equation. The second order equation because the highest derivative that appears in the wave equation is order 2. It's the highest partial derivative order that we end up taking in the wave equation. For the KdV equation, it's an order 3, a third order partial differential equation. Because the highest order of the derivative that appears in the equation is this third order derivative right here. So we will touch on PDEs in this course a little bit, but the course is really focused on developing models for ODEs and systems of ODEs and applying those results to real-world modeling problems. So the next thing we should do is talk about ordinary differential equations. These are differential equations with one and only one independent variable. But I also want to include as a caveat here, also possibly many independent variables. Oh, many dependent variables, not independent variables. There we go. So this is the main classification between ordinary differential equations and partial differential equations. Ordinary differential equations are also classified as linear versus nonlinear, and they're also classified with order, the exact same definitions for partial differential equation. In general, a single ODE for a single dependent variable we'll call it y, takes the form f of t, comma y, comma y prime, comma y double prime, all the way up to the nth derivative of y is equal to 0. Where f here is a multivariable function of the independent variable t and of y and all of the possible derivatives of y up to some order n. In where we call y a solution, y equals y of t is a solution if this equation is satisfied for all t in some interval or set I. So we have many good examples of ordinary differential equations, many of which you're probably familiar with from your differential equations class. But the idea here is that very often in models, a single ODE is not good enough. Or if you have a very high order single ODE, you can actually rewrite this as a system of first order differential equations to simplify. And this is one of the things that we'll talk about in the as we move along in the course. But what appears more commonly in applications is a system of ODE of this form. And this involves multiple dependent variables and one independent variable. So typically we have, we'll call the dependent variables, the unknowns, y1, y2, y3, up to yl. These are dependent variables. And just like before, because we're dealing with ODEs, the independent variable is t. There's nothing special with the t here that I'm using. The t could very well be x or any other physical thing that we're talking about. It doesn't have to be time, but very often in applications it is time. But it's important to make that point. So if I have L unknowns, I'll expect to have possibly then L differential equations to solve for those unknown functions. F1 is a function, multivariable function of t, all of the dependent variables, and then all of the derivatives of all of the dependent variables as well. This goes all the way up to the nth order derivative of y. L or y1 through yl. And if I have L independent variables, I expect to have L ordinary differential equations that satisfy this. that could all potentially be different as well, but that have to be satisfied in order to solve for y1 through yl. This is the function f1 is some function of all of the dependent variables, the derivatives of the dependent variables, and the independent variable. Same thing for f2. We have this all the way down to fl, where these f1 through fls could be varying very much in complexity. One could be linear, one could be nonlinear, but the idea here is that in order to solve a system of differential equations, where we are essentially solving for if we have L differential equations, or a system of L differential equations, solutions are of the form of functions of t. So we can solve for y1 of t, y2 of t, all the way up to yn of t, or yl of t, where I'll call this a double star star. This is our system of differential equations are satisfied for all t in some interval I, say. So as we move through the course, we're going to see a lot of examples of interesting, non-trivial systems of ordinary differential equations, and we're going to figure out some clever methods of solving them, solving certain examples, but also in general how to do both qualitative and quantitative analysis on various systems of both nonlinear and linear ordinary differential equations. For linear systems, there's a very, very nice theory and very, very well-known theorem that allows us to figure out the solution under very, very many cases. But the case of nonlinear differential equations is a little bit more difficult and takes a little bit more consideration. And typically in applications, when we have a very complicated nonlinear model, we're going to not necessarily be able to solve for the exact solution, but we will be able to determine properties of the solution and understand how the solution is going to behave. So we'll start off with theory of first order ODEs. And the idea here is that a single first-order ODE is the most basic differential equation that will appear in a model, and even these can be very complex sometimes, so we have to be very careful. But a single first-order ODE for y for a function y can be written as some function f of t, comma y prime is equal to 0 for all t in some set. If we can solve for a solution is of the form as we can be written as a function y of t, and this equation will have to be satisfied for every single t in the interval. Now, the theory in the book, in much of the ODE theory, involves rewriting this a little bit, solving for y prime. So y prime is equal to some function lowercase f t comma y. And as long as you do it carefully, this can be done to great effect very often, and gives us a slightly more nice way of looking at solutions to this. So we'll call this equation 1. So, like, for example, I'm talking about the differential equation y double prime plus, or I'll say y prime minus r times y equals 0. We can rewrite this as y prime is equal to r times y. And this puts it in form 1, takes it from form star and puts it into form 1. Now, solving for y prime might not always be that easy, but the idea is that this is kind of the example here. And this is what the theorems are going to be placed on the function f in terms of our existence and our uniqueness theorem. So in this class, and we'll see examples where this is violated, but for the theory, our existence theorems depend on certain assumptions on this function lowercase f. So for the theory side in our book, we will consider such ODEs. Where f is a function from some interval in t, a comma b, and y can range from c to d, and it's a function, multivariable function. So this is the set our t can range in, and this is the set that y can range in, where a, b, and c are all allowed to be possibly infinite values. So a is greater than or equal to negative infinity. It's strictly less than b, which is less than or equal to infinity. C is also satisfying in this interval, and D is also in this interval. And that's basically giving us a very wide range of possible ordinary differential equations that we can study. We can study differential equations that are population models, like we're seeing, that start at 0 and go to infinite time, and possibly have a population that's bounded by some maximum population. This is the solution axis. The population could look like this. Maybe the population goes up, decreases, and then goes up again. But this gives us a very wide range of possibilities. And we're also going to assume that at a minimum, f is a continuous multivariable function. Specifically, it's a function of two variables, t and y. And we define function y of t to be a solution of the ODE on an interval I which is a subset of AB, provided that the solution y of t stays between C and D, and y of t is continuously differentiable. For t and I. And we need this continuously differentiable in order for this equation to make sense. There are other ways of defining solutions to equations of this type. They're much more advanced. It involves what's called the weak derivative, and you can actually define more generalized solutions to equations of both these forms. But it goes to a much more advanced mathematical level of sophistication, so we'll be sticking with the theory in the book, which is the classical theory of differential equations. And what defines y of t as a solution is that the derivative of y of t is equal to this function lowercase f of t comma y of t for all t and I. So the derivative of y is equal to the multivariable function of t comma y of t at any point t in the interval. Now, for a given differential equation, you have many possible solutions, because when you solve it, you'll end up having some sort of integration constant. So what we need to do is discuss what's called an initial value problem. And an initial value problem essentially is the problem of determining that constant of integration. We abbreviate this as IVP. So an initial value problem solves in ODE while specifying that it attains or hits some initial value. And this is some point t naught y naught in the set. It's an element of the set. The rectangle from A to B and C to D. And just for abbreviation in the future, we'll call this set D. It's a two-dimensional rectangle. And we say that Y solves the IVP if it solves the differential equation. It solves this differential equation right here, or 1. And that means that y prime equals f of t comma y on I, and it satisfies the initial condition, which is that y of t naught is equal to y naught, which is the initial value of the problem. So the first big theorem that we have, that it is proved in the book, but it's not proved until chapter 8 in the book. If you want to see this, you can jump ahead, but we won't be going over this in the class because this would be a different class where you would discuss this and learn about the proof of this theorem. but it is important to write down just to get an idea of what we're working with for the mathematical theory of initial value problems in general. So the theorem is that if a function from a domain like is described above to R is continuous, then the IVP with the solution should say a solution. To the initial value problem exists with some maximal interval of existence. We'll call that alpha comma omega. This is an interval of existence that in general is a subset of AB. And this means the initial value has to be included in this interval of existence. So we can actually prove qualitatively some results about the solution. If alpha is strictly greater than A, so it's not equal to the boundary point A, then as we approach that boundary point, so as we approach alpha, the left boundary point is the limit as we go to the left boundary point. The limit of our solution has to be equal to C, our upper boundary for Y, or the limit as t goes to alpha from the right of our solution has to equal D. And we can also say qualitatively that if omega, the upper limit to our interval of existence, is less than B, then the limit as t goes to that upper value from the left is going to be equal to C, or it'll be equal to D. This is just what this theorem is definitively saying about solutions to our differential equation. Now, like I said, we're not going to prove this, but we will use this, and we will state later on in the course some similar theorems for systems. But this gives us a lot of power. In addition, right, we also have in this theorem, it's even more powerful if this function f is continuous. So if in addition the partial derivative of f with respect to the dependent variable, so with respect to y, or df dy for short, is continuous, then the solution is unique. And this is a big thing in mathematics. Investigating existence and uniqueness of a given solution. This theorem guarantees a maximal interval of existence for certain classes of ordinary differential equations, and we'll see that similar theorems can be found for systems. We won't go over the proofs of these theorems in this class, but it is important to consider for a given model. Do solutions exist, and are they unique? And some good examples applying this theorem can be found in the Kelly book. So I recommend looking in the Kelly book and looking at example 1.4 and example 1.5. Example 1.4 shows an example where the partial derivative of the f with respect to the dependent variable is not continuous, and therefore this example 1.4, the solution is not necessarily unique from this theorem. In example 1.5, it gives a slightly more complicated equation, but that does have a continuous partial derivative df dy. So in example 1.5, this theorem tells us that a solution exists and it's unique.